Hi everyone, I'm Todd Horwigan. I'm going to talk about compiler optimization with space exploration. So currently, when we do optimization in code, we take every piece of code and we use a heuristic on it to determine what the best optimization would be for it. We go through every one of them, and it works, and it's not like great, and it's worse for parallel architectures, which are obviously really popular right now. So it works really well for sequential, but it's not great for all sets of code. So the idea is for iterative compilation. You compile each code and you evaluate how well it works. So it works this works really well for function level if you compile each function with every different compilation option and choose the best. And it gets worse for suite level, so if you compile the whole program and then evaluate its performance. So obviously it's going to take longer, very large compile times, but function level does perform very well when you do this. So the space exploration approach is to search only a limited number of configurations and compile and compare them in parallel, and then choosing the best result. How we do that's a little bit different though. So to limit this, we're going to first search only n optimizations and configurations. So what that means is we're going to take an optimization that modifies parameters in a bunch of ways and choose the best n of those. And we go through making multiple combinations of all these different techniques until you end up with the n best configurations. It seems a little awkward to say, but this kind of illustrates a little bit better. So each one of these is a combination of two different optimizations and parameters for each optimization. And we go through making different combinations of those until we have the best set of those. Hopefully that makes some sense. Moving on from there, we then build a tree of all the ones that we currently have. We take whichever three perform the best in this case and make the first level of our tree. And then beyond that, we make the next level with the next set of best. Searching the tree is very simple then. You go through each layer and choose the best configuration, evaluating it after you compile. And you keep going down the tree until you have your best path. And that gives you your best configuration, which you use to apply your program after that. What's nice is that all of these are printed at compile time, so you don't have to search any of these, and you don't compile any of these programs. So the amount of compilation you have to do goes down dramatically. So one of the critical things in this is actually estimating the efficiency of the code afterwards. And so using OSC, they do only like a very simple estimator. It doesn't take very long. They only run through the code once, so it's not the best, but it does work pretty well. Improving upon that in the future could definitely improve the quality of the compilation. So comparing it to just function level exhaustive, which we went over at the beginning, it does pretty well. It's pretty close in a lot of the areas for the different tests. The red here is exhaustive search with OSC, so actually going through the entire tree and actually going through all the configurations. So in some situations, the non-exhaustive search actually performs better, and that's just based off of the performance estimator not evaluating every piece of the code. They don't get functional level interactions covered with the non-exhaustive search. Here's some more results from it. Mostly it's just that the exhaustive search is doing better in these different situations, and it works better on one processor rather than two. Any questions?
Thank you.